All right, so more on 4.5, dealing with proportions here. So as I talked about a little bit in the last video, when your data is what's called categorical binary, so a bunch of yeses and nos as opposed to numbers, it fundamentally changes everything that we've learned in 4.1, 4.2, and 4.3. And the monumental challenge of 4.5, it's a really hard section, is to redo all that stuff, 4.1, 4.2, and 4.3, with this new type of data, with what we'll refer to as proportions. So instead of thinking about it as the average number of, for example, pepperoni on a pizza, we might think about it as the proportion of people who own their home, for example. I want to start out with a proportion question that's similar to a 4.1 question. So as a reminder, in 4.1, that's where we dealt with the sampling distribution of sample averages, technically. And we're always given the population mean, so the center of the parent distribution, and we use that to find the center of the sampling distribution. And if we knew the center of the sampling distribution, we could answer questions about a sample average. If the average of number of pepperonis on all pizzas is 18, what's the probability that if I select 40 pizzas at random, the average number of pepperonis on those 40 pizzas is more than, 20 or something? So that's the idea. I want to do something a lot like that, except you won't hear the word average. You'll instead hear the word proportion. So let's start out with 4.5 example. This will be the first of many because 4.5 is a big section. And this is where we're going to deal with what's called the sampling distribution. And you're like, I'm good with the sampling distribution. Yeah, it's a different one though. It's not the sampling distribution for X bar, the sample mean. It's the sampling distribution of P hat, the sample proportion. So in the past, your sampling distribution was X bar, now it's of P hat. So, let's see, suppose 30%, I have no idea, of Irish people have blue eyes. I don't know if that's anywhere close to true, but whatever. Suppose 30% of all Irish people have blue eyes. Note that this is a proportion here. I'm not saying the average number of something, the average number of freckles that an Irish person has. It's not anything to do with averages, it's proportion. Suppose 30% of all, maybe, Irish people have blue eyes. Then I might ask you, what is the probability? And you might remember that as a phrase that kind of signifies that we're going to be dealing with the NormalCDF function. If you do, that's great, because we are. What is the probability that, in a random sample, of, let's say, 200 Irish people, more than, 35%, sure, why not, have blue eyes? All right, so I know the population proportion is 30%. So if I grabbed any number of Irish people, 200 for example, I'd expect 30% of them to have blue eyes. But not necessarily, maybe just by dumb luck in my sample, more of them have blue eyes or less of them have blue eyes. There's going to be some variance because this is a sample, not a population. And so I might ask you that if I create a sample out of 200 people, what's the probability that more than 35% of them have blue eyes? Well, what we can do is we can think about the sampling distribution of P hat. The idea is if we created a whole bunch of different samples of 200, you grab 200 people, I grab 200 people, someone else grabbed 200 people. Each of our samples would have a different percentage that has blue eyes. Right? Maybe my sample has 32%, your sample has 28%, someone else's sample has 31%. Each of our samples would have a different proportion that has blue eyes. What I can do is I can sketch a distribution where the area underneath the curve represents the probability that one of those samples of 200 Irish people has a given proportion of blue eyes. Okay, so what I mean by this is if 30% of all Irish people have blue eyes, I'd expect my sample proportion to be 30%. The center of this sampling distribution will be 30%. And actually what you'll see is we'll write these as decimals. So I'm going to write it as 0.3. But it's possible just by dumb luck that my sample has greater than 30% or less than 30%. What about 35%? Is it possible that your sample has more than 35% with blue eyes? Well, sure. Let's talk about this area over here. If I could figure out this area, this would represent the probability that in a random sample of 200 people, more than 35% of them have blue eyes. Just find this area. You're like, oh, I got this. I know how to find areas. It's the normal CDF function of my calculator. Great, it is. That's exactly what we're going to be using. With normal CDF, maybe you remember that you need to give it a lower bound, which would be 0.35 for this 35%. An upper bound, which you could use the number 1 because that represents 100%. But what we've been doing when we've been missing an upper bound is putting in a bunch of 9s. It'll turn out that 1 is a sufficiently large number, but I'm going to use a bunch of 9s just to be consistent with what we did in the past. So 9999 for my missing upper bound, and then my center, then my spread, and then I'm done. Right? If I just knew center and spread, put the center here, the spread here, I'd be done with the problem. It would give me this area, and that would be the answer to the question. So really what this question comes down to is recognizing, oh, I've done these before. Recognizing that you know how to do these questions, and to do all these questions, all you really need to know is what the center and the spread is. What I'm going to ask you is for shape, center, and spread. Because I'm a little bit picky, and I would like you to justify why you were able to draw this shape as approximately normal in the first place. If it's not normal, you can't use NormalCDF. So, not a bad idea to justify why it's normal. We'll talk about why in a second. But then if you could just give me the center and the spread, we'd be done. Well, I've already labeled the center. We know it's 30%, but maybe that deserves a little bit of talking before I just put that in here. The center and the spread of the sampling distribution of sample proportions is this symbol and this symbol, right? They're the things that used to be mu sub x bar and sigma sub x bar, but it doesn't make sense to call it mu sub x bar because it's not the sampling distribution of x bar, it's the sampling distribution of p hat. So technically, and I'm not too hung up on this, I don't really care if you mess it up, the symbol for the center is mu sub p hat, and the symbol for the spread is sigma sub p hat. I'm not super worried about those symbols. I'm more worried that you can figure out what numbers those are equal to, because those numbers are going to go right here, and without those numbers, you can't answer this question. So what is the center? What is mu sub p hat? Well, in the past, when it was mu sub x bar, it was super easy. Right? It was just equal to mu. It used to be true that the population average of the sample averages was just equal to the population average of individual observations. It's kind of the same idea here. Just like this is the easiest formula ever, mu sub x bar is just mu. It's the same idea here. Mu sub p hat is just equal to p. What is p? P is the population proportion. And p is given to you in the problem. 30% of all Irish people have blue eyes. That tells me that p is 30%. I'll write everything as decimal, so it's 0.3. What is the probability that in a random sample of 200 Irish people, the sample size, we used to use the letter N for that, we still do, more than 35% of them have blue eyes? Here's that 35 right here. Right, this is telling me where to shade. So hopefully, with this P and this N, I can figure out my center and my spread. The formula for mu sub P hat is it's always just equal to P, and P will always be given to you in these problems. So it's 0.3, which is why I put 0.3 in the middle right here. What about the spread? Spread was the tough one in the past, right? Sigma sub x bar, you had to remember this formula for it. It wasn't just sigma, which was given to you in the problem. It was sigma divided by the square root of n. And you might think, oh, it'd be nice if we could do that same thing over here. Well, we can't, because sigma is the spread of the parent distribution. It's how spread out individual observations are. But we don't have a spread of the parent distribution over here. How spread out are yeses and nos. Like there's no notion of spread here. They're either yeses or nos. Since the data here is not numeric, we don't have anything that's like a sigma over here in this case. But it turns out that we do have a formula to talk about how spread out our individual sample proportions will be. Right? You got 200 people, maybe 31% of your sample have blue eyes. Someone else got 200 people, 28% of their sample have blue eyes. How spread out are those individual sample proportions? There's a formula for it. And if we calculated standard deviation by hand, this formula would make a lot of sense. If we calculated standard deviation by hand, I'd be able to explain to you this formula, but we don't, so I can't. So you kind of just have to memorize it. Because first I'll write it up here. This will be a memorization thing. I try not to make you memorize too much stuff. You might be shaking your head right now, but this is one of those important things to memorize. This is equal to the square root of, oh, you can remember that because there used to be a square root here. P, cool, that's given to me in the problem. I'm not too worried about that. Times 1 minus P for some reason that I can't explain unless we come up with the formula for standard deviation by hand, which we don't, divided by n, our sample size. What I'm saying is the spread of our sampling distribution of sample proportions is just based on n and p. If you know n and p, you can plug them into this formula and figure out the spread. And a nice thing is those are exactly the two things that were given me in this problem. N was 200, and p was 0.3. So the spread is just the square root of p times 1 minus p divided by n. So in this case, it is p is 0.3. 1 minus p would be 0.7. And then n would be 200. And I'm fine with you leaving it just like this. Maybe for this first one, I'll calculate it just to talk about what this means. But generally speaking, you can leave it just like this. And note, before I go off pulling out a calculator and doing calculations and losing anybody, we're kind of done at this point. Right? To figure out this probability, all you needed was recognizing that this was the lower bound. There was no upper bound. And then the center and the spread. Center and the spread. If you have these two formulas memorized, then as long as I give you n and p, which I will in every single one of these problems, you could find these areas. Normal CDF. So let's do it. Let's calculate this just so I can talk about what this means, even though I don't really need you to calculate this as a number. So we'll take the square root of, try again, the square root of 0.3 times 0.7, that's the 1 minus p, divided by 200. Note that as long as this is all one term, you don't write plus or minus anywhere in here, then you don't have to worry about the order of operations. It still all works out perfectly. You hit enter, gives you this answer. You're like, whoa, it seems like I messed something up there. What's that mean? I'm not used to getting some weird decimal for the spread. In the past, it's been numbers, right? The spread up here was like 2 or 3 pepperonis. Here it was like $20,000 or $30,000. What does it mean to have this weird answer here of, maybe I should say approximately, 0.0324? Well, what this means is when you're drawing this distribution, if you were to count up and down by the standard deviations, you don't do that anymore. That's the beginner way to draw these pictures. You're an expert now. Instead, you write shape, center, spread off to the side. But if you were to count up and down by the standard deviations, 30% would be in the middle, and you'd be counting up and down by 3.24%. 30%, 33.24%, 36.48%, 39.72%. And then you'd count down by 3. This is the standard error. In other words, the standard deviation of your sampling distribution. Anyways, let's answer this question. Normal CDF 0.359999. My center is 0.3. And my spread, rather than put in this decimal approximation, I'm going to put in this whole mess just to make sure that rounding error doesn't change my answer by enough that the homework gets picky and marks it incorrect. Normal CDF function is still in the distribution menu, so second and then variables, still the second thing listed here. The lower bound, as I wrote above, is 0.35. The upper bound, there is no upper bound, so any sufficiently large number will do. 1 is sufficiently large in this case, but I'll put in a bunch of 9s. My center is 30%, so 0.3, and my spread is the square root of 0.3 times 0.7 divided by 200. Note that it's perfectly fine to put expressions in for one of the arguments in this function. It's no problem at all. The calculator can figure that out. Hit paste, hit enter, it spits out this number, 0.0614. Or if I asked you to format it as a percentage, round it to 2 decimal places, you'd say 6.14%, and you'd be done with the problem. That's the idea with these problems, is you're looking for an area, so you're going to be using normal CDF. When you're using normal CDF, you need lower bound and upper bound, which are given to you in the problem, and then the center and the spread. And the center and the spread will come from these formulas that hopefully you'll have memorized. To get full credit on this problem, not only do you have to tell me the center and the spread, you also have to justify why the shape is normal. So I talked a little bit about that in the last video. I don't even want to get into it too much. It's the n is greater than or equal to 30. Unfortunately, that criteria doesn't work anymore, so you got to memorize a new one. That's a bummer. It's one of the many bad things about 4.5 is there's a fair amount of new memorization to do. But it's the last of the big memorization sections. If you can just get these things down, you'll be in good shape. So just like I want you to memorize this formula, I want you to memorize this criteria. Of the two, this one is way more important, because this one you actually need to put it into your calculator to get this answer. If you don't know that formula, you don't know the standard error, the standard deviation of your sampling distribution. So you can't figure out the answer. So it's kind of a big deal. If you don't know this formula, it's not the end of the world. Like, you can still draw your picture. You just lose like 1 point on a 20-point problem. But if you're looking for all the credit, the reason it's normal is because n times p times 1 minus p is greater than or equal to 10. And you could check that if you want, but frankly, I don't even need you to check it. As long as you know this, I believe you that you could type numbers into your calculator. I believe you that you could take 200n and multiply it by p, 0.3, and multiply that by 1 minus p, so 0.7, and check that you get a number that's greater than or equal to 10. So that's our criteria for normality, center, spread. Here's your picture. That's what all the questions of this first type look like in 4.5. And you're like, no, you're forgetting something. You just did normal CDF. What about inverse norm? Well, you could do inverse norm questions. There's nothing inherently wrong with inverse norm questions in this section. They're just really hard to word. It's hard to talk. How would you word that? I'd have to say something like, what percentage is so high that there is only a, 5% chance that a sample of 200 Irish, that in a sample of 200 Irish people, the proportion of people with blue eyes would be higher than that percentage. Like, it's really hard to say in English, so you don't find very many of these questions out there. There were none on your homework assignment, so I promise you I won't ask you any inverse norm questions in this section. How about that? Just be normal CDF. So 4.5 is broken into 3 different parts. This is what I call 4.5 normal CDF because all the questions use the normal CDF function. There's one minor little trick that I could add to this. So let me do one more question here and show you how I could change this. So same premise. Suppose 30% of Irish people have blue eyes. Let's keep all of this the same. What is the probability that, let's keep that the same, in a random sample of 200 Irish people, that's all the same. And then let's pick up right here. What if I said between 50 and 55, say 60, 65, let's get a big number. 50 and 65 of them have blue eyes. And you're like, oh, okay, this doesn't change that much stuff, right? Instead of more than 35%, instead of giving me the lower bound and no upper bound, and I put in the 9s, you're giving me the lower bound and the upper bound. Yes and no. Yes, I am, but I'm not giving you them in terms of proportions. I'm giving you them in terms of numbers. This 50 and this 65 do not go directly in your picture. You have to figure out that this is 50 out of the 200. What you have to do if you are asked this question is say, oh, when you say 50 right here, you really mean 25%, because 50 divided by 200 is 25%. And when you say 65 right here, you don't mean 65, you mean 32.5%. Whoops, can't write and talk at the same time. Where'd that 32.5% come from? 65 divided by 200 is 32.5%. I guess if I wrote that one as a decimal, I should write this one as a decimal. The point is just one of the many challenges of 4.5, and this is not just in the normal CDF stuff, this will also happen with confidence intervals and hypothesis testing, is sometimes in the problem, they tell you the percentage that you're interested in. Sometimes in the problem, they give you the numbers, and you have to convert those into percentages. So my shape, center, spread would be the exact same in this problem. Maybe this should be green or something. But when I draw my picture, it's going to look a little bit different. That's a weird one. I still want 30% to be in the middle, but now I'm shading between 25%, so put it anywhere out here, it doesn't really matter, and 32.5%, put it out here. I can tell you from experience that what a lot of people do is they throw 50 here and 65 here. But you have to be careful. We're dealing with proportions here. So you don't care how many people have blue eyes. What you care about is the proportion of the sample that has blue eyes. And to answer this question, it's just another normal CDF. The lower bound is not 50, but 0.25. The upper bound is 0.325, 25%, 32.5%. The center is still 0.3, and the spread is still this obnoxious formula, the square root of 0.3 times 0.7 divided by 200. Take your calculator and you type that all in. If you're lazy like I am, you might just pull up the most recent entry. Might have to do that a couple times. Here we go. This is the normal CDF one. That's still my spread. That's still my center. My lower bound is now 0.25. And my upper bound is 0.325. So I got normal CDF. Lower bound 0.25, upper bound 0.325, center 0.3. Spread this mess. Hit enter. It'll spit out this area, which is 71.84%. If I ask you to format your answer as a percentage rounded to 2 decimal places, that's what you get. Comment here. Everything's a decimal, right? In the past, this was a little bit less confusing because these were numbers. Think number of pepperonis or income or something like that. And these were the decimals. And when you saw decimals, you thought area, and it helped keep everything straight in your head. Now that's not the case. Now these things are themselves decimals. So decimals both represent the numbers that we're interested in at the bottom of our distribution and the areas that we're shading in our distribution, which makes this pretty challenging. I think that's just about all I have in this section. Maybe just for completeness, one more thing I'll add, although I think you would have probably figured this out on your own. If I said less than 35% up here, right, then 35% is the upper bound, so the 35% goes right here. And I don't have a lower bound. So you might think that 0 would be what you'd put in here, and 0 will be perfectly fine. 0 is a sufficiently small number that it'll work. But what I typically put in is negative 9999. So the same tricks we did in the past where you're missing an upper bound, you put in a bunch of 9s, missing a lower bound, put in negative bunch of 9s, will still work in this section. So it's easier for you to connect this with 4.1 by doing it that way. It's not a bad idea. All right, that's all I got.